Everything that you turn off the lights. You want to see the screen, but
You want to really?
start with the side.
Yeah. Okay.
You guys see that well? Or should I wait a second?
Wait another 20 seconds. That looks good.
Sweet. Good morning, everybody. Welcome to our senior design capstone presentation. Thank you all for being here. I'm sure that Friday, 8 a.m. finals week, this is where you want to be. So thank you and welcome. I'm Amit Abdrahim. I'm here with Dylan Alcorn, Jacob Burks, Maximilian Kowalski, Jacob Goldschmidt, and Thomas Hackbarth. Before you, we have two different senior design groups under the advising of Dr. Seabass. So we have it all combined into one presentation. As for the agenda, it's going to be an introduction, just brief. I didn't want you guys to sit through two different introductions about what SAE Baja is. So with Seabass's direction, we did this. And then we're going to go into the suspension team with the questions following, then the drivetrain, and then those following questions. As for what is SAE Baja, SAE is the Society of Automotive Engineers, which is the professional organization that develops standards, publishes technical reports, hosts industry events like tours, talks, etc. Previously, SAE was solely focused on the automotive industry, but now its mission is to advance mobility, so aero, etc. SAE also hosts different collegiate competition series like Baja, Formula Hybrid, Formula SAE, Clean Snowmobile, and Aero. As for the objective of Baja, the objective originates in 1926 based off of the Baja California Peninsula, where people build and race souped up vehicles in land races, whether it's 500 miles or 1,000 miles. And as for SAE Baja, the goal is to engineer and fabricate a single-seat off-road vehicle designed to compete in 4-hour off-road endurance races. This simulates real-world engineering problems and practices like submitting requests for proposals, etc., and then those associated challenges like hearing back you did something wrong from the judges. And then for the competition structure, teams from universities ranging from LA to Sao Paulo to Gazabia all participate in 4-day national events. Some include the hill climbs, the maneuverability tests, the acceleration and braking, as well as static events like the design presentations, cost reports, and design evaluations. A bit of the history: SAE was founded in 1905, 2 years after MSOE, I believe, so we're a bit older. Primarily, as I said, serving the automotive industry, but now it's changed. Baja originated as the Recreational Ecological Vehicle Competition or contest in 1973 based off of Dr. William Shapton, I believe. And then in 1976 is when it became the Mini Baja competition. So there were 4 different competitions spread across the country. And nowadays, since 2007, it's formerly known as SAE Baja, where 100+ teams from around the world come to compete at our nationals. And then MSOE Baja has a strong history of being a part of the Mini Baja series, if you may or may not know. We have first place competitions dating back to 1980, and that's really where we'd like to go back to in the future. So thank you. I'm going to turn it over to the suspension team, and then we're going to head on down.
So thank you, Mead, for that fantastic introduction. Once again, I'm Maximilian Kowalski. To my right, that's Jacob Goldschmidt and Thomas Hackbarth over there. So yeah, we'll walk you through the rear suspension redesign that we've kind of done in conjunction with the drivetrain team. So to introduce you guys, this year we're creating a new chassis. The whole Baja team has already designed a new chassis, and that includes already an interim suspension design that's kind of incorporating the old style drivetrain that we were using with CV axles. So one of the key aspects of the drivetrain team that they wanted to revise for the drivetrain side of things is incorporate a load-bearing axle setup with U-joints instead of that CV axle assembly. So that's one of the kind of key aspects of our redesign that we wanted to incorporate their contribution to that. In addition to that, we wanted to improve on the old vehicle suspension setup, which was incredibly overbuilt. While it was robust and strong, it was definitely heavy, and there was a lot of performance gains that we could make just by reducing the weight. So that was kind of the two key areas where we focused on, reducing the weight and incorporating that new drivetrain design.
Yeah, so with this project, we had some objectives and constraints. Our objectives included having 0 toe gain throughout the suspension travel. We also wanted at least 10 inches of suspension travel, at least a 25% weight reduction compared to the previous Big Red rear suspension. And then we wanted to have it withstand competition conditions, like a rough terrain that we'll have to go over very quickly, which would be very hard on the suspension. So, and then our constraints that we had to follow the rule books, or we had to meet all competition regulations. It had to be compatible with the drivetrain solution of the load-bearing rear axle, and also it needed to be compatible with the existing chassis, but we can't move around any tubes or, yeah. And then also we wanted a static toe of 0 degrees. So, yeah.
Going into our geometry research, firstly, we looked at the trailing arm geometry. Trailing arms are quite simple and typically utilize a single pivot point from the chassis. The pivot of the trailing arm rotates about the center line of the vehicle. This yields slight changes into the toe gain and negative camber as the suspension compresses. Next, we researched semi-trailing arms. Semi-trailing arms are quite similar to trailing arms, except that the mounting of the pivot is slightly offset from the center line of the vehicle. This yields much greater changes in toe and camber and allows for a little bit more optimization through the angle of the pivot onto the chassis. And we also wanted to consider different geometries. So we looked at the McPherson, which is typically utilized in the front suspension, but when repurposed for the rear, the steering bar can be removed, and typically it is mounted to a unibody chassis with a strut. But for our case, because we're using a load-bearing axle, we could change that strut mounting to a ball joint or a pivot joint, so it's not over-constrained. Next, we looked at the single control arm suspension geometry. This is not a typical suspension geometry that you find on a lot of vehicles. How we found out about this geometry is observing other competition, such as Purdue University's most recent vehicle. With the implementation of a load-bearing axle, which utilizes U-joints instead of CV joints, which the drivetrain will cover in more detail later, the lower linkage of the double A arm can be removed, yielding us just a single control arm. And that gives us the lightweight benefits of only having one control arm while still having the ability to optimize negative camber while still yielding almost no toe gain. And yeah, moving on to our materials and manufacturing. Firstly, we looked into DMLS printing. DMLS printing utilizes CAD modeling in order to create and design certain geometries, and then this is imported into the computer as a .stl. It creates layers of powder that is sintered together, and then some benefits of DMLS printing is that it has no restriction on the design. If there are cavities or certain features that are behind certain material, it's able to produce this. And typically after the design is made, there are supports and the surface finish might not be up to spec with certain interfaces such as a bearing going into the knuckle. So there are certain treatments that need to be done after it is printed. Typically, this utilizes aluminum silicon 10mg for a material to print out of. This is a really high quality material to print. It has great flow properties and works great for printing with DMLS. Then next we're looking at casting. Oh, sorry. We're also working with Evology, who utilizes this technology and many other manufacturing processes. When we asked Evology the recommendation, they recommended us this aluminum silicon 10mg. We also asked for a quote for a previous knuckle that we used in previous designs. And they quoted us at $3,800, very expensive. Yeah, and next, another process we looked at is casting. With casting, the mold is created with a negative dimension of the desired geometry. And with this mold, multiple components can be easily remade, which is desirable. If we were to make copies of the same component, or if a component were to fail and we need a replacement. This also utilizes aluminum silicon 10mg for casting, or 835-6 can be utilized for the same reasons. They have good flow properties and their ability to handle wide temperature ranges without cracking. Some downsides to casting is that because of cooling rates, mold shrinkage, and material flow, these are factors that you have to consider, which can produce inconsistent parts that require machining and treatment after the process. Next, we looked at CNC machining. This produces highly consistent parts with high tolerances and great surface finishes, unlike casting and DMLS printing. And because CNC machining produces components that doesn't have issues like casting and DMLS printing, which has porosity and anisotropic properties, that's just not a problem you have to worry about CNC because you're starting with the raw material. There's no great changes in temperature. And with CNC machining, typically you utilize 661T6 aluminum, which if you were to go the DMLS or casting route, wouldn't be a great material selection for DMLS printing or casting, but it's really good for CNC machining. And 661T6 has much greater yield and tensile strengths comparatively to 835-6 and aluminum 10 mg. Lastly, we looked at 4130 chromoly tubing and metal fabrication. With 4130 chromoly tubing, you can create components with much greater tensile and yield strengths when compared to the previous mentioned alloys. This is important with high loads that are acting on members such as a control arm due to the long length and moment that occurs on these components. And in order to fabricate with this material, we would have to utilize metal fabrication, which includes notching, bending, and welding. And since as I mentioned, it has such high strengths, this material can be formed into tubular members and still be lightweight while maintaining strong properties. With all that in mind, we went to work on modeling and ideation of different concepts.
So we decided on the single upper control arm suspension system, which utilizes that single upper control arm. And we came up with a few different ideas for that, and we scored them based on 3 criteria: weight, manufacturability, and strength. Weight was our most important criteria because that's one of our objectives of reducing the weight of the suspension system. The 3D printed aluminum one scored the highest because of the freedom of optimization. We can do any geometry we want with that. We can make it have optimized strength to weight. And then one that also scored fairly good is this 3 steel tube design, which only utilizes 3 tubes, and that's the benefit because we don't have any of the welds between the 2, and it's higher strength than like the 5 steel tube because it doesn't have the welds, which create stress concentrations and weak points. With manufacturability, the 5 steel tube one scored the highest because of its simplicity of just having the straight 5 tubes. You don't have to bend them to a perfect angle or anything. And yeah, and then one that didn't score very high on that was the machined aluminum because we have to have complex structures for machining. And writing on the G code and stuff for that. We quite a project. And then strength, we scored the machined aluminum one the highest because of its being machined out of billet aluminum and it had very good properties. So, and then we ended up choosing a 5 steel tube because of the ease of manufacturability and fairly good weight and strength properties.
Next, moving on to our knuckle concept designs. Firstly, going over weight. The 3D printed aluminum concept that we have designed seemed to be a good candidate because you can optimize with AI technologies and FEA analysis in order to create complex geometries that machining billet aluminum or machine and welded steel components you're probably going to be able to create. Next, we're looking at manufacturability. Also, we gave 3D printed aluminum probably the higher score just because Evology is thankfully sponsoring us. We're very grateful for that. So we don't have to pay the expensive cost for DMLS printing, and we just have to send them a .STL and very easy to manufacture. And then looking at strength, the billet aluminum knuckle was probably the better concept to go with in that regard, just based on the natural properties discussed earlier in our background section. And in the end, we went with the 3D printed knuckle just because we favored weight. Our whole design is to try and decrease the weight and the unsprung mass in the suspension just to get better handling characteristics out of the vehicle.
So our final design includes that single upper controller suspension system with the straight 5 steel tube control arm and the 3D printed aluminum knuckle. This combination best complements the use of the load-bearing rear axle because of it doesn't over-constrain that. And then, yeah, this will provide us with very good weight reduction compared to the previous suspension. So that's what we are doing. And the hardware that we've chosen for this include a 5/8 inch diameter shoulder screw for the control arm to knuckle connection, and the one is circled because that one is going to see a lot of shear force. So we wanted that one to be very strong. And then for the shock upper and control upper and lower connection points, we want 3/8 inch by 16 bolts. And then for the control arm to chassis connection, it's 7/16 by 14 bolts. And then for the bearing, for the wheel bearing is a 3206 double row angular contact bearing, because that'll be strong in axial forces and radial forces, which with the use of the load bearing rear axle, they'll see a lot more axial force than typical wheel. And then with the suspension systems, we got 10.97 inches of suspension travel, which is seeing how high up at full compression, the distance between the bottom of the wheel and the top plane, and then going at full droop, and the distance between the bottom of the wheel and the top plane. And that gives us almost 11 inches of suspension travel, which is better than our objective of 10 inches. So.
Yeah, so once we had those final design decisions made, we wanted to kind of examine in a preliminary way how they would fare in a few common scenarios, or I guess I would say extreme scenarios, but unfortunately they're very common for Baja. So that's something that the two kind of ones that we chose to analyze were the curve strike. Now, there isn't a lot of curves necessarily in Baja, but one thing, one of the pictures earlier that when Tom was kind of introducing our objectives is we'll have a rock crawl test, for example, right, where the vehicle is climbing up these rocks and it might slide and encounter a lateral load kind of near the bottom of the tire. So that's going to introduce a large moment force going through the suspension, as well as introducing an axial force in that load bearing axle. And then in the jump load case, now jumps are very common, but we wanted to examine kind of a jump that would put a lot of stress to the system. So, and actually this also happens very often, is a landing off axis on a single tire. So here we chose a 60-degree angle of impact with the ground. And all that load is 2.3 Gs times the entire weight of the vehicle going through that single tire on the jump load case. So, as I said, they're very preliminary analyses, and one of the kind of areas where we actually had to do a lot of work in was actually getting these CAD models to function inside of ANSYS. So we want to just kind of see how these would fare. And on the right over there, you can see how we set up the curb strike, which was, it ended up being, due to that large moment, 5,000 pounds going in plane with the A-arm. And then we've constrained it where it attaches to the chassis. And we've given a bit of freedom in terms of rotation at the shock mount. But that's how we've constrained that curb strike side of things. And then in terms of the jump, we've analyzed that load case at the reaction force of the spring when that A-arm is going to be going, or when the suspension system is going to go under compression due to that jump. And here's how the results turned out. Now they're a bit, you can't really see where those maximum stresses are actually hitting, but that's kind of one of the things that I wanted to note about these preliminary analyses is just that we're getting primarily stress concentrations at the fillets meant to approximate the welds. So for our curb strike load case especially, we're hitting at the moment, we have 150,000 PSI of stress in that small weld region, where the rest of the part is actually faring just fine. So that's one of the areas where I believe that load case would benefit from some refinement. But at the moment we are getting results, so that's definitely an improvement on where we were earlier in the semester. And then in terms of the jump load case, this one seems to be a bit more robust. We are at 67,000 PSI in terms of the peak stress, and again at a stress concentration. And as you can see, yeah, the part otherwise is deforming as expected. So yeah. So there's our A-arm, and then in terms of the knuckle, we apply the same load cases. So in this case, for the curb strike, we're now looking at the reaction force where that knuckle attaches to the A-arm, and basically in the opposite direction. And then in terms of the jump, we're applying the jump force load through the hub where it would actually transfer that force to the knuckle. And in terms of these analyses, so again, now one thing I want to note about the knuckle that's different from the A-arm analysis is that we're now using aluminum in this analysis. And so for the curb strike, again, that part isn't doing so great at the moment. And again, we're kind of in that region where there's a bit of, there's this kind of hole included for weight savings purposes. We're getting along the edge of that, we're getting a lot of stress. So that's something that we could potentially look at in terms of, one, once that load case is a bit more refined, we can determine more accurately how we're doing on that curb strike. But then again, that's a potential point of where we might want to refine the design as well. Now, in terms of the jump, this one's doing a bit better, where this part isn't going to be failing in terms of maximum tensile stress. But again, just like with the curb strike, we're reaching peak stress around that cutout region. So that's something that we want to examine in the future.
So yeah, looking at the weight improvement we got from this new suspension system, we saved a lot of weight in the control arm and the knuckle. The previous design weighed almost 19.52 pounds just for that control arm and knuckle, compared to our new design that only weighs 4.53 pounds. So we saved a lot there, and then also a little bit with the hardware, which makes for overall design is 34.2% lighter than the previous design, which will help a lot with it's reducing the unsprung mass of the system, and will, as like the car goes over bumps and stuff, it will send less reaction forces into the chassis as the wheel goes over bumps and stuff. And in summary, we met some of our objectives of the suspension travel and weight reduction. We have to do further analysis to work on the eliminating toe gain through the suspension travel. And also we need to actually build it and test it to be able to determine if it can withstand competition conditions, like the races and suspension tests. And then we were able to build it within our constraints.
Yeah, one thing I want to touch on the previous slide there in terms of objectives is just that in terms of competition conditions, of course, once we run it at the event, that's when we'll finally get our true test of that side of things. But of course, we want to rerun that FEA and kind of make sure that we can approximate that as best we can. And I guess that's what I want to talk about with the next steps that we plan on making for the upcoming semester. So we didn't really talk a lot about the kinematics in this presentation, and that's just basically focused on kind of researching overall geometry, seeing what works and what doesn't with that load-bearing axle setup that our drivetrain team wants to implement, as well as working with all the constraints that we have. And then of course focusing on just saving weight from our current concept design. So that's kind of where our focus lies. Now that we have a basis for where we want to iterate from, we want to run that optimization in terms of defining exactly all the lengths and moving potentially mounting points along the existing chassis tubing, somewhere where we can, by the end of the next semester, we can tell you all about the change of degree per inch of travel and all those dimensions that we would like to talk about. So once we have that ready to go, then we'll modify the CAD models to actually match those new dimensions that we're going to define. And then we'll be able to run a more refined FEA analysis that's going to, more accurately model our actual load kits that we're going to be running through. And then since those dimensions are going to be changed, those load paths are going to be slightly different as well. So that's going to potentially bring up new areas of that we're going to be interested in potentially strengthening or refining through that FEA analysis. And once we're done with that, we'll be able to manufacture and put on the car in May. Any questions? Thank you for listening.
Thank you. Right on time.
I have
was
some
it?
questions.
Was that time?
Yes.
Awesome.
Yeah, I have some questions.
Yeah.
Yeah.
Oh, is there-
Your suspension travel, seemed like the droop was greater than the compression, is that correct?
Yes.
Does that mean that it's non-linear stiffness? Like, does it get a lot stiffer as it goes, or?
Well, it was all measured based off of the top plane, which is the like the bottom of the chassis. So it should be able to go further down and
So you're gonna set it up differently than maybe with those numbers?
Yeah, it's gonna be a little different because
you wanna have more, you're probably gonna have more G's upwards on the tire than.
yeah, it's basically just where I measured from.
Okay.
rather than-
Okay, so those are sort of like, just you have 10 inches of travel to play with and you can set it up.
Yeah.
Later as you need. The load case of the curb strike. Yeah, curb strike sideways is probably a real common kind of thing.
Mhm.
And what I've seen is like if cars are sliding
Yeah.
on the track and they slip into a rut, these are not like nice flat roads.
Right.
They have all kinds of whatever. And so that sideways kind of hit on the bottom is real. That's an important load case.
Yeah.
A lot of car to break, so concentrate on that one.
Yeah. Yeah.
I have a comment about showing the FEA results.
Mhm.
If, like, you chose the pictures to show,
Mhm.
and you said yourself, it doesn't show it very well.
Right.
You need to pick something that shows your results
Okay.
really clearly. And I would like to see, you showed the part, but I had no clue, like, really what I was looking at. So show the assembly, like, there was a slot in the knuckle
Mhm.
where the high stress was.
Yep.
But for me watching, I had no clue what's, like, is that an open slot or is there another component there that's bearing on there?
Right.
Causing that stress? And then show the load, the constraints on your model
Mhm.
and where the loads are applied real clearly before you jump into the stress results. That would be my
Okay.
suggestion next time you want to show those.
Sounds good. So just more clarity in that.
Yeah, like, because I'm coming at this completely blank slate and you're showing details, which makes sense to you because you know the context, but I want to see, this is a part in an assembly,
Okay.
what is causing this stress before you jump into the result.
So a couple of things related to what Dr. Shaver just mentioned. For the finite element analysis, it would be better if you conclude the takeaway from it. So for instance, was it one meter stress that you are presenting? And then how does it compare with yield? Because you're looking at a worst case situation. So if you're using that to gauge your factor of safety, where are we landing? With the knuckle, you have already concluded we're too close possibly to the yield. So we may need to do something. So something similar as a snapshot out of the slide saying that, okay, so the conclusion is A, B, C, and this is what we need to do for design. A related thing, so those are two load cases you picked, that's okay. But then you also need to comment on static failure and dynamic failure. Both need to be considered. You may not have done the fatigue calculations yet. Want to have some approximation of what you expect out of the new design versus the old design. A static calculation is good, but your system is a dynamic system. It has to last an X number.
Yeah, that's a good point. Yeah.
Well, the second question I had, maybe you partly answered it in your future scope, is about the dynamic model of the suspension system. So you do need to have a dynamic model where you can see how it compares with your current system. And that's both the kinematics and dynamics of your suspension system.
Yeah, that's something that we're going to be early in the upcoming semester working on actually developing. It's just not something that we had the opportunity to get to at the moment, but yeah.
You guys have access to the OptiStruct software? Or not? OptiKinematics?
We do often view the formula
Yeah.
team that's using, so we're looking to take advantage of that for our optimization.
And that allows you to model. You don't need to optimize, but at least model and see what your system capabilities are with respect to kinematics and dynamics.
Yeah, even if you can pick one simple load case that you could do in the parking lot and model it, and then when you have the car, drive it and see how they compare.
To make sure
Drive up onto a curb at 10 miles an hour, seriously.
Yeah.
And if your model can predict that, it's good for maybe other things as well.
Large organizations want to build modeling and simulation capability over time. So Baha, you have a lot of continuity in the team. So if maybe one of these teams builds a model that they're reasonably confident in, then the subsequent teams will be able to build up on that model and do a lot of prediction and simulation up front.
That's actually, yes, that's actually something that we'd really like to build up to have something. It's something that we've been speaking about with Amit as president, is just having a lot of documentation for the upcoming teams to work with. So I guess we're kind of starting off that process, since coming into this, we didn't actually have a ton of FEA load cases or any of that stuff to go off of. So we're kind of developing all this stuff fresh, but yeah, thank you for your feedback there.
And last question was about DMLS. Do you know how much time it will take to print?
They said about 2-4 days turnaround time, so it's fairly quick. Yeah.
And the post-processing is time consuming for DMLS.
Yeah.
Depending on the shape and contours of your part, the organization is going to do the post-processing as well for you?
Yes, correct.
That's great.
All right.
That's
Thank
all
you.
my questions.
All right, thank you.
Yeah. So with that, we'll introduce the drivetrain team. Move to their side of the presentation.
Sweet, welcome welcome to the drivetrain portion of the presentation. Once again, I'm Amit Abdurrahim, that's Dylan Alcorn and Jacob Burks. As for our problem statement, our objective of this senior design is to design, fabricate, and analyze the components for the drivetrain for the Baja team's new car, Onyx. Our goal for this is to design the drivetrain, the gearbox, and the load-bearing rear axles. And these modifications are aimed to improve our performance at national competitions. The improved drivetrain combined with our weight reduction with a new chassis should fare very well for us. Bit of an overview. Our goals, all components should be removable within 30 minutes. And with Big Red, you needed to take out the CVT, the engine, then the gearbox, and then you could pull out the drive shaft. I don't think we could get out the rear CV axles even, so being able to actually hot swap things on track and within that time frame is really, really important for us. We're doing 4-hour endurance races. The more time on track, the more opportunity we have to win. The entire driveline must be at least 30% lighter than the previous iteration, which was coming from Big Red. And then the driveline must withstand Baja racing conditions for at least 50 hours. And then as for constraints, the drive axle must be a 2-inch inner diameter, and that comes from Amalgam Composites. They really don't like manufacturing anything less than 2-inch diameter. I got that constraint moved or removed for the driveline. I just thought that 2 inches with that driveline was way too much, and luckily they were able to do it for us. Components must not interfere with SAE safety shrouding, such as the hazardous release of energy components, CVT guarding, etc. And then we wanted our low fidelity prototypes due on the 20th of next month. We were expecting to go to the Blizzard Baja competition. However, due to the team budget and not wanting to rush things and make them right, we canceled that plan. And then the carbon composite cannot be fit to the bearing. Kind of makes sense, but going into this, we did not know that. Getting to talk with Dan from Amalga, just barring concerns, etc. And then the current drivetrain, this is the model from Big Red. With this vehicle, we used the CVTech CVT to a 2-to-1 reduction box. And then we used a solid steel drive shaft with purchased Can-Am differentials and Can-Am CV axles, which was, if you know Baja, way too heavy, way overbuilt, not what we need. So moving forward as a team, we really want to focus on in-house design and development. That way we can be prosperous as an organization. And then for the driveline, my main goals were to reduce the weight of the drive shaft by over 50%. This is really, really possible. Currently, my expected is around 65% reduction. It went from a solid steel shaft to carbon composite and aluminum, so I can't imagine it would be anything less. I also wanted to be able to remove it in 15 minutes. And then the constraints primarily is the HROE, which is safety shrouding around the drivetrain. You need roll hoops, and it's specified by SAE. That takes me into the decision matrix. There's the flanged carbon shaft, the dog box, and the solid shaft. These are all weighted on machinability, serviceability, performance, and weight. These are all equal weight. And then the flanged carbon shaft is the one that won, especially with being able to remove the shaft from the driveline. And then the dog box is also being investigated by the driveline sub-team. Based off of just the timeline of senior design, I didn't want to rush that. And also, yeah, I thought it would be fun for the team to be able to work on. In the future, with that dog box, we're hoping to use carbon composite and those flanges once again. So this senior design is kind of a test bed for what we're going to move into in the future. And then my initial script, this is just an initial prototype MATLAB script that goes through a range of torques compared to the RPMs over the various CVT ratios. This is initial script just using 6061 T6. This code also calculates shear stresses, factors, and safeties all throughout that range, and then tables them out. It's a fully adjustable code, so you can change the CVT ratios, you can change the reduction in the gearbox, you can change the range of RPM and torque. And that RPM torque range from the Kohler engine was grabbed from a previous senior design. Yeah, and then with that, all the results are displayed and stored. As for Autodesk Helios, this is the main tool that we've been using with our industry partner, Amalga. It is a Autodesk suite for primarily composites. They use it all the time for their composite drive lines. So this is similar to FEA. It's designed to help engineers predict behavior of composite structures under specified loads, similar to ANSYS with FEA. With Helios, you can analyze components to really high detail to optimize your performance or your just designs, period. We solely focused on the tomb and beam analysis with Autodesk, with Amalga, as that is their bread and butter. That is their entire business model almost. However, Helios can be used in a bunch of different applications. It can range from automotive with drive shafts, panels. Nowadays, it's a lot of EV battery storage. Aerospace, rotors, wings for stunt planes, etc. And then sporting goods, carbon composite bikes, carbon composite golf clubs. People want that. If I could golf, I would. And then it also goes into the material modeling. It allows users to define the properties of both the composites, the fiber, and then the composite matrix and the fiber matrix, so how it's actually weaved, and then the type of weave, whether the angles and the amount of weaves you have is dependent on or what sets your strengths. This allows you to determine different failures as well, including delamination between layers using the virtual crack closure technique and the cohesive zone method. It also just goes through a bunch of general failures like the maximum stress criterion, the Sa-Wu failure, the Hashim failure, and the multi-continuum theory. And then I just did some initial bearing stresses. These are using the estimates from the initial code that I had written. They're going to have to be redone, but it does reference equations from Shigley's mechanical design with a bearing life of around 1,700 hours or 1,785 hours, which is perfect within our spec. And then due to pitting concerns, I also did gear stresses for the front bevel box. I think it might just be because I was using a really cheap gear and it wasn't hardened. So due to that, we're going to have a submerged bevel box, but moving forward, we'd like to have a better gear. As for the material choices, our prototype is going to be 6061 T6. We have it in the shop. It's free. And then the final is going to be using 6061 T6 for the flanges that are going to be mounting to the bearings. And then the black amalgam composite from Amalga Composites, that's their proprietary blend with all the properties on the top. And then also the commercial carbon that Amalga uses, it's just their general carbon weave. It has really great properties and fits for all we need. And then moving into the gearbox.
All right, so for the rear gearbox, I included a couple of big pictures so I can get you familiar with the system a little bit. So this shaft here will be where our CVT input is, and then down here, and you can see it in the other view, will be where our drive axles will come out, and then this is the split to go up to the front wheel drive portion. It also has an integrated center rear brake instead of having the mount board. Since we're doing the load bearing rear axles, we need to integrate that into the gearbox as well. So we'll have a brake mount in there as well. And then we went through a design matrix. We were thinking about different options for how we could make this reduction possible. We went through chain drive, belt drive. We ended up deciding on a geared reduction. The chain drive is pretty difficult to maintain. If any of you know the green car, that one used to be a chain drive and it was a nightmare. It's also a little bit limited performance, and with that system, it was super heavy. And then belt drive, we have enough problems with the CVT as it is, and that's just one belt. We don't need to add like 3 more. So I have seen other teams run it, but they typically don't perform very well either once it gets wet and muddy. So we decided on a gear reduction. It's a lot lower maintenance, basically just change the oil after competition if you don't break anything. It's a lot better performance for us. And then as far as material goes, we selected a 6061 aluminum, just like everything else basically. We've done it before, basically every single one of our gearboxes has been aluminum. It's pretty cost effective. We can machine it here. Like I said, previous usage, and it's also pretty lightweight for the size. And some of our improvements, we're going with lighter weight. I can pass this around if you'd like. We 3D printed this just as a concept. We can do some general fitment in the chassis with it, if you guys would like to see that. So the combined weight is the previous version because it had a differential separate from our actual gearbox. It was about 90 pounds. And with this, we're targeting less than 50. So it'll be a significant drop, not only just actual mass of the full system, but rotational mass as well. So it should be a lot better. Also has smaller overall dimensions compared to the previous system. It's a lot easier to remove as well. And we'll have a lot more room around it to actually service it too. So there's a chance we might not have to remove it in most cases. As far as our reduction ratio goes, we selected 8-to-1. Previous was 2-to-1, which we kind of just looked into that the other day. I'd taken that gearbox apart a bunch of times, and it was designed by a previous team, and I just never really thought, oh, this reduction is horrible. So we did some reduction calculations. So it's like we had 7.2, 8, 10, 12, and then between the CVT minimum and maximum ratios. We selected this 8 because it gave us a decent top speed, but also allowed for a lot more torque on the low end. We've had a lot of issues with that in some of the hill climb sections. Now we know why. The 2-to-1, that was great. But it also allows the CVT to use the full ratio range. So we've had problems where even if we have that 2-to-1 gearbox, we're not reaching the top speed we were hoping for because the CVT isn't fully locking out because it just doesn't have the torque to do it. So up on the top, I have our old system, and then down here on the bottom, I have our new one. So we selected the gearing and then developed this housing. So I'll have a section view of this box later, but just overall size is a lot more compact and packaged a lot better. Be a lot easier to maintain, like I said earlier, and then reduce rotational mass. So in this section view, you can see there's a lot of wasted space in this gearbox, and I made it really heavy. So instead of that, this you can see is a lot tighter pack. So it also allows for better lubrication throughout the competition. Because this one, we've just basically set a pool of oil in the bottom and just hope it got to all the gears. This one will actually have surface for it to flow around. And then I did some FEA on these, so some stress concentrations. Obviously, this box up here isn't very good for stress concentration, so we reduced a lot of those with some fillets and rounding around the gear profile. And then we did some displacement resistance, and the 6061 appears to be performing well. So these are just some initial FEA checks. I did a torsional load on the front wheel drive forward section. A lot of teams we've seen run into something and then their whole side of the case will just come off. So we wanted to make sure this would actually survive an impact like that. And this is really common if you're going up. They'll set up like the concrete road barriers and tell us to drive up them. And the first initial hit into it is usually pretty tough on the car. So I basically just assumed, let's say the front wheel stopped and your engine is still spinning. And did a deformation check to just see how that would affect our gearbox. So I assumed these were solid mounted here and then put a rotation on that shaft. Our maximum deformation was well less than 1 millimeter, so I don't think we have to be concerned about that. But there is a stress concentration right here, and we can add like fillets or something else to blend that out. One of the reasons we haven't done fillets a whole bunch on some of these other surfaces here is because it's going to be a lot easier to CNC machine, and it'll take way less time if we have less fillets.
Sweet. And now moving on to the rear axle.
All right, so on the right here, on the right here is the picture of a U-joint that I had gotten from a supplier doing research for these U-joints specifically. And on the left side is the U-joint that I had drawn up in SolidWorks as a prototype of needs for any simulations or if we must machine ourselves. So while we had generally agreed on choosing to implement and use the U-joints, I did some more research into not only just the U-joints, but the CV joints or constant velocity joints we had previously used on the car in the older model of the Red. I researched 2 commonly used types, the Zephyr constant velocity as well as the tripod types. To compare them against the U-joint as I'm going through, determining machinability, serviceability, and all those listed on the decision matrix. The U-joint had met very well the serviceability that we were looking for in terms of being able to simply remove 2 pins from the U-joints to be able to do any sorts of maintenance, whether that's changing out bushings, changing out the pins themselves. We're able to just simply
We'll move the axles to the side after those two pins are taken out, and we can do most of the work from there. Compared to the CV joints where it would have had to need removing the actual axle, so then we can start to work on the actual joint itself. However, there is a drawback to these U-joints. They have limited articulation for angles and aren't able to go to the kind of extent that those CV joints were able to as well, which puts a restriction on how long we can make these axles in our final designs. So the prototype of the rear axles will be using 4140 steel for the U-joints. Ideally, we hope to reach out to the previously mentioned research supplier known as Apex Fastener to hopefully get at least 2 U-joints, so then we can do some testing and understand how they will react to certain loads. But if we have to, at least we'll know what steel to use to machine them ourselves. The physical tubing we'll be using for the axle is going to be 6061 aluminum, because that's just everywhere in our shop. The final product will be using Amalga's carbon fiber composites as our tubing for the physical axle, and we'll be using the 300 series of the Apex Fastener as shown below on the bottom left. The data sheets above here, this is just a description of what torsional and strength values these U-joints will be able to do from testing done by the supplier, as well as a description of what that U-joint is going to look like in terms of the outside diameters and overall length and weights. The following calculations are a collective sum of equations I had determined would be necessary for the analysis of the U-joints and axle. The allowable pin shear stress is meant to do analysis for those pins that will be experiencing a lot of the shear and force within the U-joints themselves. The critical buckling for the load and stress of the axles is also important because they will also be carrying weight. Another one is this bottom equation here of the loads and moments on laminates. I just didn't have a real good name for them like the others. But what it does is it's using a compliance stiffness matrix as shown here, the values A, B, and D, to relate mid-plane strains and curvature of the composite axle to any of the forces and moments that it's going to be experiencing while in use. This stiffness matrix will be made up of values from the material properties of said composite.
As for the next steps, final driveline measurements just off the Baja team, their requirements, where they put the front bevel box and where the steering goes. That just kind of depends on how long my drive shaft needs to be. And then we need to communicate with Amalga for the driveline and axle manufacturing. They're already completely on board and have been great partners. Just once we get those final measurements down, we can get it out to them. And then ordering materials, which will lead into the in-house manufacturing, CNC, the new CNC lathe that is coming, which is going to be really cool. Standard lathe, mills, and bonding. The HROE, which is the hazardous release of energy design, needs to be done. And then 5-star race car bodies should be making that out of composite as well. Additional FEA, like translating from SolidWorks to ANSYS, etc., refining our load cases. I also need to do some FEA on the bearings and the drive shaft, and then ordering U-joints into the manufacturer. Questions? Hopefully.
Plenty. Just interested, that's all. What the heck is a dog box? We were talking about that and I had no clue what you were talking about.
So it's basically like
So one of your
typical, yeah, so think typical power transmission like couplers. We call it like a dog box, it's more of like a slam box. It's just modified couplers to.
It would be good to show
Okay.
what you meant, like,
Okay.
in general, for both of the groups, like, more description of what your design options were
For sure.
would have been helpful to me.
For sure.
So we kind of jumped right into, here's our decision matrix, and I didn't know what those design options really were.
For sure.
So yeah, no, that would help.
Wants us to switch to rear-wheel drive only?
Yeah. So it's going to be our 2 to 4 wheel drive actuation within the drive shaft.
See, during the presentation, I had no clue why. We went to 3 options. How much torque is coming in
It
and
was-
going out?
Through the drive shaft, it was expected around like 5, or the range was some 5 something foot-pounds. We don't have that fully defined yet because that's going to be based off of what we actually decide on CVT and then the final gearbox ratio, which is the 8 to
So
1.
you're coming, your part of the system is whatever's coming from the CVT?
It's coming, well, it's from CVT to gearbox, well, engine CVT gearbox.
That
And
would be
then,
helpful too, like, kind of just jumped into individual parts and define your system, like, is input to your system is what, from the engine, from the CVT, where is that? What are you designing, what are you not designing? Would be helpful, rather than jumping right into the details, so.
for sure.
What's torque is coming out from your system?
It's 1795 pounds per inch, I believe it was.
Pounds?
Yeah. And that was translated through the bubble box.
Okay. So that would be like a general explanation too, for like the stress analysis.
Definitely.
Where are your loads coming from? And about how much are they? If you're designing a drivetrain, those are numbers you should just like have from day one at the top of your head, what's coming in, what's going out. What the speeds are, how they're going. We made our last one. No, I have 2 more questions. You said a couple of times about 6061, it's free, or 6061 is very cost effective. To get a billet of aluminum to make that, where is the muffle? Do you know what that would cost?
Yeah, the pieces of those, we got the ones for the front gearbox or the front bevel gear. Those were about 170, I believe. And for that size, it's probably going to be 250 a piece, and we're going to have 2 of them scram piece as well. So.
And you're going to make turn most of it into chips.
Yep.
Yeah. The plan was originally
So, I
to
don't
go to Scott
argue.
Forge, and they were going to give it to us for free, but they've been.
Yeah, that's fine for the Baja team, but as a senior design project, I think you should kind of be aware of what the actual cost of your stuff is. Because that's good engineering, is to keep track of your actual cost. And if you get it donated, if Umaga is donating composite, that's fantastic. But as a senior design project, you should be aware of what the cost of that thing is that you just designed. On the FEA, you had one result that you said, the deformation on the case was less than 1 millimeter. So that was okay. What would, I don't know where that deflection was, but what would not be okay?
If it's moving a lot, I would say more than 1 millimeter, it's probably going to start tearing out of the bolt holes. I'm going to work on some fatigue analysis on that as well in this next semester to try and, I also want to simulate going off of jumps like we have in the suspension team, because that whole weight of the gearbox is going to be bouncing on the actual mounting points somewhat. So I want to develop those further next semester.
It's always good to look at the stress and the strength, but when you present deflection as a result, that's important. But I had no idea 1 millimeter. I don't know if that's good, bad, if it's 10 times better than it needs to be, or if it's about to fail because it's going to impinge on some other part of your system.
Yeah, and
So
one good thing
explain
I
that a
noticed
little
with that
more
is
if you could,
increasing the load case didn't alter that result very much, so that's also pretty good.
Yeah, but if if you're going to give a result, then whether it's like fatigue or stress or something, what is your criteria for this is good, bad, or marginal?
Sure.
So 1 millimeter doesn't really have a meaning if you just give it as a result by itself.
And also if it's total deformation or directional, what direction is it actually deforming makes a difference.
So stretch the deformation comment Dr. Schaefer made, general aspiration is infinite rigidity in the gearbox. So we want to minimize the deformation or deflection as much as possible. Setting a goal and then saying how far we are from the goal. Sure. I only have one question. You started with the design goal of 30% lighter and 50 hours of life. Does the design accomplish?
As of now, yes. In the drive shaft alone, it's a 65% reduction. With the gearbox, it was even greater, I believe. And then even more on the axles, we went from solid CDs that were really heavy, purchased off shelf, to now what we have. I don't have the exact number, but we've definitely reached that goal.
And the life?
Yes, as for all the bearing calculations so far, life has well exceeded it. And then with that, it also gave the operating life that I targeted with was about 6 races and then a handful of test days, which is the typical like 2 seasons. But it seems like it will run for many more.
The axles and structural pieces will have to define a duty cycle.
Yep. We still need to run through all the fatigues and the actual like life cycles of materials.
So I
Fatigue is gonna be for next steps, yep. All right, thank you.
I don't know who's driving this.
It says
Yeah, I want to use it. Your call. For a minute.
Well, we can move this so you can stand here with the rest of us. We don't get shoved in the corner.
Whenever you're ready, go ahead.
Hi, I'm Liam Anders. I'm Alex Thompson. I'm Kyle Tommy. I'm Rob Redmond. And we are tasked with designing the next generation of the Formula Hybrid suspension for the MP7. So we started by defining a problem statement. And the first thing we wanted to do is define our scope. So it is front and rear suspension. This is important. Some designs in the past have only done front or rear. So we need to make that clear. The next thing was defining our goals. So number one, we wanted to decrease weight. The MP6 suspension was on the heavier side for a Formula car. And the other one was increased performance. This is done by measuring our higher lateral acceleration in both high and low speed turns, as well as trying to quantify ideal squat, dive, and roll. And then lastly, the last bit of our problem statement is defining the time frame, which is to have the suspension on the car by the St. Patrick's Day Parade, which is a traditional Formula Hybrid team goal to get a fully running car by then.
So looking at the key pitfalls of the previous car suspension, the primary one, as mentioned before, was weight. The total weight of our in-scope components for this project was 46.2 pounds on the previous car. Looking at other top teams at the Formula competitions, this looks to be typically under 10 pounds, so we are looking to greatly reduce that. Along with the poor dynamics that the vehicle was seeing, our drivers reported a very heavy steady state understeer, along with an on-throttle snap oversteer that we are looking to tune out of the car. So the scope of this project that we decided to look at was our A-arms, our belt cranks, our push rods and pull rods, and our pickup points for the suspension on this new car we are all able to change. And due to budget constraints, we will be keeping the same wheels and tires, the same shocks, and the same uprights and braking assemblies.
So we needed to define a few constraints for the project. The first of these Liam briefly mentioned, but we need to have the suspension on the car and built by March 17th, the St. Patrick's Day Parade. The next constraint is regarding rules compliance. We have to meet all the rules that Formula Hybrid sets. The first of these being the minimum wheelbase. So we have to have a minimum of 1,524 millimeters wheelbase. We also need to have a maximum of 25% different front to rear track width. So that's the width of the front tires and the width of the rear tires. We also need to have a minimum of 2 inches of suspension travel, 1 inch up and 1 inch down. And we need to pass the tilt test. So here's a good picture of what the tilt test entails. So the car sits on a tilt bed and it gets tilted up, and it has to not tip over at a minimum of 60 degrees. So we need to ensure that the car will pass the tilt test. We also need to make sure that our suspension is compliant with the MP7 chassis. This is a new chassis this year, but we still need to make sure that we can actually put our suspension on this chassis. So given these constraints, all 4 of us could break off on our own and come up with our own individual design concepts for the suspension. So on the upper left, you can see that's what we refer to as the traditional pushrod suspension. The upper right is a pull rod. The bottom left is the cantilevered pushrod, and the bottom right is the single shock suspension.
So first up is the cantilevered pushrod, so named because the belt crank mounts to a post that is cantilevered through the frame. This design is most similar to the MP6, kind of saying, what if we just used a very similar idea and see how it fared? The pros of this are that the team already knows how to manufacture all the parts, and we're familiar, we have all the tooling. And then in the rear, the packaging is very good. As you can see, the shock mounts right up against that frame rail, out of the way of anything that might be in the engine bay. Cons are the front packaging. We're going to have some electronics that go up in the front underneath this nose cone area, and having a shock there isn't as optimal as it could be. And then the other main con is the fact that since the belt crank is cantilevered through the frame, it puts a lot of torsion in the middle of that frame member, where you get a lot of torsion, and then any compliance in the chassis is not great.
So the second of the designs is what we call the single shock design. This is mostly derived from typical road-going car suspensions, where they have the Pearson style suspension. So as you can see, this single shock connects to the lower control arm, and then also an upper support structure. And the biggest upside of this design is the inherent linearity, as it's not reliant on the extra geometry of a belt crank or a push rod or pull rod. Therefore, the shock travel relative to the heave of the vehicle will inherently be very linear. But the biggest downfalls are the adjustability and mostly the adjustability on this one. So unlike the other designs, motion ratio cannot be changed easily without a redesign of the control arm itself to move the shock inward of the chassis or outward of the chassis. And then also, if the motion ratio were to be changed as the shock gets moved farther in towards the chassis, that puts a lot more bending on the control arm itself, where the mounting point would be. Otherwise, the packaging would be good, as it keeps the suspension outward of the chassis, away from other component structures.
The third design we came up with is the traditional push rod. So this design is very similar to the cantilevered push rod in the sense that the bell crank and push rod design translates the vertical motion of the wheel into the shock motion. Some benefits of this design are that everything is very accessible. The shock is high up, so you can make shock adjustments easily. You can make ride height adjustments easily due to the location of the push rod. You can corner balance the car better. On the rear, the push rod is mounted to the upper control arm in order to make enough room for the axle to pass through to the wheel. Some downsides of this are also the fact that it's mounted up pretty high. That's offsetting, that's moving the center of gravity up a little bit. And on the rear, the very shallow angle that the push rod makes with the upper control arm is going to negatively affect the amount of force that's going through the push rod.
So the last concept that we decided to evaluate was a pull rod suspension design, which is very similar to the cantilevered push rod, except instead you're mounted to the top bar and pulling down here. So when your wheel heaves up in your motion, you're able to compress your shock with a second class lever belt crank on the bottom. The advantages of this design is not only keeping everything outboard of the front of the car, we have things like electronics and bodywork that are looking to go up on top where a lot of the front shocks are mounting. So by being able to keep everything outside, we are able to allow those places more space to sit, along with being able to keep all our weight very low, the belt crank and shock being the primary heaviest parts of this assembly. By being able to keep them outboard on the low side of the car will give us the lowest center of gravity. However, the disadvantage of this comes in the rear of the car when the pushrod suspension cannot be mounted above both of the A-arms. So the CV axle would have to pass through both the shock and the pull rod to get to transferring power to our rear wheels, making this design likely infeasible for the rear of the car.
So the first of the criteria we looked at when weighting these designs is the weight of each design. So we analyzed the weight of each design, both through the forces in the members or components of the designs and the size of each component in the designs. To analyze the weights through the forces, we related forces to the required strength of each component within each of the suspension designs. And therefore, we relate the required strength to the inherent weight of each component. So if you move to the next slide, we chose a 500-pound load case, which was somewhat of an arbitrary load case. We considered that the prior weight of the vehicle was about 1,000 pounds with driver in it. So we chose for a one-wheel load case acting normal to the contact patch of the tire, 500 pounds. And each chose the same track width for our suspension designs to analyze the forces through components such as the control arms and the push rods mainly. After analyzing those forces for each of our designs, we were able to look at the differences, which ones had significantly higher forces going through them, and then which ones were similar. The designs with similar forces going through them were mainly weighted based off of the size of the components then for the weight. And then the components that had significantly higher forces than other designs, those were weighted more based on the force and the inherent size and strength that the component must see. And then the second of our criteria was linearity. We looked at the linearity of the shock motion relative to the heave of the vehicle. And these four lines on the spot are corresponding to our four different designs. And typically we fit them to a power law. Typically the power we would like to get as close to a value of 1, because that is perfectly linear shock motion to heave of the vehicle. And then we rated each of these based on their value and where they were farther or closer to a power value of 1. So for the values here greater than 1, those are progressive, being that the suspension will get slightly stiffer throughout the travel, and then this value below 1 is digressive, where the suspension will get slightly less stiff as the travel increases. And we rated these designs based off this. The single shock is inherently the most linear, as there's only the shock and the angle of the shock making the travel nonlinear. And then the other designs we looked at which one is furthest from 1 got the least weight, and then between these two similarly distanced from a power value of 1, the digressive was weighted more poorly than the progressive, as ideally we'd like the suspension to become more stiff rather than less stiff throughout the travel to prevent bottoming out.
So moving into our third, fourth, and fifth criteria that we ended up putting into our decision matrix, these are the more qualitative decision matrix points that we decided to go through, the first of which being manufacturability. We looked at the complexity of the things, whether we'd be able to do them on a 3-axis Bridgeport or a lathe that we have on campus, or if we would need to outsource them to either a vendor that sponsors us, such as Avology or Emulga Composites, that would have to be able to create that and dig into our budget that we are allotted from those companies. So the more we are able to make in-house and the faster we can make it, the better it is for our timeline. The next we looked at was our adjustability. We are not modeling any transients in our suspension and our simulations, so being able to change things such as toe, camber, caster, our overall motion ratio, our spring rates, and our damping ratios very quickly. This is something that we'll be able to do to be able to get the most out of our short amount of testing time that we get with this vehicle. The last of which was the packaging, which we had mentioned a couple times earlier. This has to do with its cross dependencies and other subsystems, being able to give them as much room as possible on the much smaller vehicle that we are creating this year, and being able to make sure that the suspension is feasible to be able to fit onto the car.
So after we were going through all of these criteria, we could build our decision matrix. So we assigned each one of them a weighting factor. We gave manufacturability the highest because we need to actually be able to produce this and put it on the car. We gave packaging the lowest value. And then we went through and scored all of these designs and split them front to rear due to various feasibility issues between the front and the rear of the car. So we scored them 1 to 10, and that ended up giving us a pull rod design on the front of the car and the cantilevered push rod on the rear of the car. So we did a little bit of testing as well to go along with this to continue the feasibility aspect of this project. So the first testing we did was determining the center of gravity height. Now, because the MP7 doesn't exist yet, we were using the previous car, the MP6, to get a baseline of center of gravity height. So what we did is we put the car on as level of a surface as we could find, and we put it on scale pads. And we got a baseline overall weight of the car, front to rear bias, left to right bias, cross weight. And this was a good starting point for us. So in order to determine the height of the center of gravity, we would pick up the back of the car to an angle of 20 degrees. The whole car would be at 20 degrees. And we would scale the front end of the car. And that would give us a different number for the weight on the front of the car compared to if it was sitting level. So we could put these numbers into a spreadsheet, and we ended up determining that the center of gravity height on the MP6 was 10.4 inches. So we could use this to continue on the feasibility aspect of this and essentially determine if the car can pass the tilt test. So we started off with 10.4 inches as a CG height, did a little bit of trig, and found out that in theory the car should be able to tilt to an angle of 68.57 degrees with that center of gravity height. We needed a little bit of leeway based on where other components are going to mount in the MP7. And so we estimated that the center of gravity height on the MP7 is going to be 12 inches. So we reran the numbers and ended up with 65.64 degrees as for a tilt angle on the tilt test. So either way, with both of these, the car should be able to pass the tilt test. We also needed to make sure that the car was rules compliant. So we ended up choosing a wheelbase of 1,552 millimeters, and this was partially constrained by the chassis as well. So this was essentially the minimum wheelbase we could get without interfering and having non-ideal pickup points for both the front and rear suspension. We also needed to figure out our track width. We needed to determine if the front or the rear was going to be any different, and if they were going to be different, they needed to be a maximum of 25% different. We ended up going with the same track width front to rear because we didn't see a reason why not to do that. That simplifies a lot of the calculations that we need to do. We also need to ensure that the suspension travel is a minimum of 2 inches, 1 inch up, 1 inch down. So in order to figure this out, we took our motion ratio and our total shock travel. So our total shock travel is 2¼ inches. Multiply that by our motion ratio of 1.5, which is kind of the standard that we've been shooting for, and we ended up with a total travel of 3.38 inches.
So moving into what we're going to be doing next is defining our pickup points. So as discussed, the chassis has already been designed, so we're limited to a large degree, but we can move where exactly our pickup points mount within the nodes on the chassis. So as you can see in this picture, they're not perfectly centered, and we've been playing with moving them. this changes our roll center and camber gain based on where they sit against each other. But obviously, the further from the geometric center of a node you get, the more chassis compliance you get. So trying to balance all these things is what we've been working on.
So once we have those points pinned down, we are able to then estimate the forces through those beams. So we were able to obtain force and moment data from the Formula SAE tire test consortium, which relates things like slip angle and slip ratio at set tire pressures and inclination angles to lateral force, longitudinal force, and aligning moment being produced from those tires. So by creating our load cases for corners we know this will have to go through, such as a maximum acceleration, a maximum braking, and a slalom, we are able to use this data to see how much force that each tire will produce to each beam in the members, which can be plugged into Optimum G to quickly solve, which we can use to then see exactly how strong those tubes need to be. Along with that tire data, we are also able to create a 2 degree of freedom millikan moment method simulation that relates side slip angle and overall steering angle inputs to the moment produced around the center of gravity of the car, along with the total overall acceleration, to be able to produce a graph such as seen off of Plackville's car that we were able to take for this example closest to me here, where you can see when the car is at trim, which has 0 moment around the center of gravity of the car, we are able to see how much lateral acceleration we can pull out of the car. And by taking the Simulink model and adjusting our total lateral load transfer distribution, we're able to find where it will be best to create our slight amount of understeer by putting this point underneath this line, creating the maximum amount of lateral acceleration, and then based off of that lateral load transmission, along with our target ride frequency and roll gradient, we are able to be able to choose our spring rates and our anti-roll bar rates. Once we have these chosen, we can go into choosing our damping rates.
So in order to do that, we need to know what damping characteristics our shocks have. This was done using Hayes Performance, one of the team sponsors, and their shock dyno. So the shocks that we use on the car are actually mountain bike shocks. They were originally made by Manitou, one of Hayes Performance's companies. We took them back there and had them tested. The graph on the right shows that we took all of our 4 shocks and set them all to the same damper settings and ran a test. And the 4 lines are seen there just to make sure that none of them have gone bad or if there's anything wrong, just to be like, yep, these are all the same. So we can use 1 shock for all our tests, which is what we did here, where you have the black line is 1 damper setting in rebound and then compression, and say the red line is another one in compression and then rebound, just to get an idea of what you're looking at, comparing resisting force that the load cell in the dyno measures versus the velocity that the shock was being actuated at. This data was then taken into MATLAB and kind of rearranged into a more usable form, because each of those lines was for a given damper setting, and we wanted to rearrange it to say, these are our damper settings that we can choose from, and then have a function that relates force to velocity for each of our damper settings. So say rebound setting number 24 out of 27 is this blue line here that relates our force to our velocity for that given clicker, and then we can adjust it as needed, but knowing what to design around a midpoint so that we're not designing the suspension and then having our dampers also like, oh, we need to run it at 27 or else it's useless. And all other 26 settings just aren't usable and we can't. Any questions?
Thank you. Yeah, I'll do a couple of quick ones. One minor comment, it would be nice to have slide numbers so we can refer to the number for the questions. But no big deal, but I guess maybe I saw it for traditional push rod, it seemed like it scored high on both front and rear. I guess my question, if I saw that right, is it 31, 33? So would there be a benefit maybe of using the same setup so you can maybe learn something from that?
I suppose there could be slight benefits to having the same front to rear to be able to understand how they interact and maybe possibly make the force analysis similar. However, I think the increase in points that we see in the pull rod and cantilever outweigh that fact.
For the tilting test, I guess, do you guys think about, you have some really good ideas of testing and all that, calculations are good. What about just testing the tilt itself? I mean, 2 floor jacks, lift it up,
We've been brainstorming how to do that safely in the garage.
That was our biggest concern was keeping a driver in the car and not having it go with the tilt test. They strap the car in, so if it does tilt, it'll stop. And we couldn't really figure out a good way to do that in the garage.
What do you think about it? Yeah. I was thinking about the floor jacks, you can lift it, but it's a good point, safety, yeah. For the dampers, what was you said the damping was set at something? Was there like a certain number that they used?
So,
And how did you get that number?
The shocks have clickers in them. It's hard to tell in this picture. There's these knobs here that change your compression setting. So we ran tests at various settings and then interpolated the data to get what the relationship between force and velocity is for each of those settings.
Oh, so you did do different settings? Oh.
Yep.
All right. This is the last question. I'll say good analysis, good testing, everything. Have you done any like response analysis? Any dynamic kind of response analysis on the dampers themselves?
We have not currently. We know what our target damping ratio and compression and rebound are going to be, and then once we are able to pin down our spring rates off of the simulation and our target roll rating and ride frequency, we will go from there in terms of transient response.
As a plan maybe for next.
Yes.
All right. Sounds good. Yeah, thanks.
A follow-up question on the spring rates themselves. So can you choose? Is there a range of spring systems with the suspension that you can choose from?
We have 5 total spring rates that we are able to choose from in our garage. So we will be balancing all those variables with the spring rates that we are having.
So once you narrow that down between the spring constant and the damping constant, you can get closer to a full dynamic model of the system.
I believe so, yes. Currently, it is not modeling any role in the chassis or simulation. It's a static simulation, but I would love to break it into 4 corners eventually.
That's all.
All right. Well, thank you.
We have a couple of annotations where it's like semi-transparent notice. We were in here last night and it works better if we have just the outside lights on. That enough light for you guys?
Oh, this is good.
Okay, perfect.
I think we're ready, right? So final presentation right on time. Go ahead.
All right, my name is Ryan. I'm Hubert. I'm Paul. And we're the SMG3 manual conversion design team.
So let's start with some background research about the SMG3. It is a sequential manual transmission. It is 7-speed, and it is a single clutch automated manual transmission. And this transmission is found in about 33,000 BMW models. And this unit uses an electro-hydraulic control unit to move the shift forks And in this figure with the white background, it's label number 5. That is electrohydraulic unit. And on the bottom right here, we have the full assembly, which is mounted on top of the transmission. And these are the shifter interface mechanisms.
All right, so to start off talking about what the SMG system actually is, this is kind of a high-level overview of the components. So we have the transmission itself, obviously attached to the engine. We have the electrohydraulic pump. Then we have the user interface. This is what the driver interacts with. And then on top of the transmission, we have the hydraulic control unit. So this is where the solenoids actually move the shift forks in the transmission. And as we said before, the SMG transmission is mechanically a manual transmission, but it is actuated by hydraulics.
Yes, so this leads to our problem statement. The electrohydraulic shifting mechanism found in the BMW is known to decrease the reliability while also negatively impacting the drivability and driving enjoyment. So our project statement is it will replace the electrohydraulic mechanism with a novel mechanical linkage, which will result in a standard H-pattern driver interface.
Prior to beginning any physical design, we first needed to research what all goes into a well-rounded shifter.
So conveniently, Ryan actually has the SMG3 transmission. So some of the first 2 weeks, we measured the force through a handheld scale. We use this at an approximately 30-degree angle, and we attach it to the shifter interface. And on the figure table to the left, you can see all the values for forces calculated through these. And we noticed a peak value of 236 to 233 newtons. So we use these calculations for further development.
The next thing we did to research this project was to use a handheld 3D scanner to fully get all the geometry of the SMG3 transmission, as well as the interior console and trim, to see what geometry we were limited in. So using the scan, we were able to zoom in on the shift selector portion where the electrohydraulic unit mounts. We were able to pull the bolt pattern off of the transmission using the 3D scan. And using this, we're able to determine the maximum area that we could use to design our transmission interface to fit within, as shown in that figure there. Additionally, we wanted to look at several different cars to see what a sporty, good, well-crafted shifter would feel like. So to do this, we looked at 5 different vehicles. We looked at a couple 5-speeds, or 1 5-speed, 3 6-speeds, and my neighbor 7-speed out of his C7 Corvette. And what we were looking at with this project, or with this experiment, was to analyze the total lateral or left to right travel, as well as the left to right lateral force to move over to the desired gear, as well as the travel from 3rd gear to 4th gear example, the total engagement travel, as well as the total force to engage a specific gear, as well as disengagement. And some of the cars had different interior trims that limited some of our data capture, but we were able to test all of these vehicles, and we determined that the C7 Corvette had the most well-crafted shifter. You couldn't have your gears spaced too close together, such as with the short shifter, it was very easy to get lost between gears. And on the contrary, with like the older Supra, the gears are spaced so far apart, it felt like you're shifting a truck. So having them spaced close together, having the total engagement also close, would give us a well-rounded shifter.
All right, so this research culminated in our objectives and constraints. So based on the geometric research that Cole was just talking about, we decided that the lateral movement or the left-right movement of the shifter should be a total of around 50 to 115 millimeters. Now this was a range that we found of the tightest 6-speed that we could find, which was a short shifter, and then the widest shift throw that we could have while still maintaining a sporty feeling was 115 millimeters. This range is wide, but it's constrained by
it's constrained by geometry, which we'll talk about later in the user interface. But these ranges are basically the ideal range. We did the same thing with the longitudinal shifter movement. Now this is the distance between two gears. So if we're say engaged in first gear and you shifted to second gear, this would be that distance. Again, we found some cars which were very short at around 60 millimeters, and the longest acceptable range for us would be about 115 millimeters. Again, we're now moving to the neutral lateral force. So this is while the shifter is in neutral, if you move the shift lever over to a different gate without engaging the gate. So that was between 3 to 10 pounds, and that depends on how many gates you're moving over. And we'll talk more on that in a couple slides. So this is the big one, the longitudinal shift force. This is the amount of force that it takes to push the hand shifter into a gear while the car is stationary. Our goal is to be under 14 pounds. This is the maximum amount that we measured without being uncomfortable. Then an overall goal for the efficiency of our linkage should be 80% input force to output force. So this accounts to all of the friction that we are experiencing in our different translation mechanisms. So the goal is to be 80% efficient. So that brings us to our constraints. This is the stuff that we have to meet these constraints. So the output throw of our transmission linkage must be 8 millimeters. This is to match the stock SMG transmission. The linkage must fit completely within the transmission tunnel. So this is the constraint that, or this is the area between that is currently taken up by the hydraulic control unit that BMW designed. All components must mount to the transmission, the chassis, and the interior without modification. We must incorporate a reverse lockout to prevent accidental engagement. And we must include a fail-safe lockout, which ensures that two gears can never be accidentally engaged at the same time, even if there was a single component failure of our system. Finally, our goal is to have all components operate within their fatigue limits for ideally infinite service life, but at least as long as possible.
And that brings us into our design procedure.
So starting with the transmission side mechanism, I'll briefly explain all of the design ideas developed by the team. The first one is a Rolex. As you can see, it is not feasible at all. It consisted of a rotating gear mechanism, which did not pass much testing the criteria. The last one right here is the link reverser, which uses a latching mechanism to transmit the motions. And the two contenders which stood out was the twin cam and the quad cam. So ultimately, we went with the twin cam setup because we believed that we could switch the quad cam mechanisms, two of the quad cam mechanisms to simple reversers. And some of the criteria that was most important for us was manufacturability, packaging, and qualitative force transmission efficiency.
Onto our driver interface mechanism design matrix. The criteria here was manufacturability, complexity, packaging, qualitative force transmission efficiency, lateral force integration, and then overall integration with our transmission interface mechanism. So we had three different contenders here. First was the single rod. That would be equivalent to the stock manual shifter that came in very few M5s, and that tested very well initially, but its overall integration is what killed it. To make it work with, it would work with that Rolex shown in the last matrix, which is not feasible at all. The next is the 4+3 hill shifter. I stole that from the C4 Corvette, which had the 4+3 Nash, which was a 4-speed with a push button on top of the knob. That'll give it an overdrive, making it an extra 3 gears for a total 7 gear overall. So to do that, that would have the shifter would sink down based on a detent for a specific gear, which would activate the lower selection rod. That would transmit that force to the transmission interface mechanism, which was not really feasible either. And then that brought us to our final winner, which was the gated 4-rod output shifter.
Right, so here is the gated four rod shifter that or gated four rod output shifter that we were just talking about. As you can see, the driver interface is gated, as you might have seen in some exotic cars. So basically we have one input from the driver. We have a number of gates. Each of these have 3 positions, so you can be in neutral, engage forward, or engage backwards. Then we have the 4 output rods. Each of these output rods can either be in neutral, which is centrally located, engaged outwards, or pulled inwards. Then moving over to our transmission side mechanism. This mechanism contains several individual sub-mechanisms, each with the goal of translating the driver interface shift pattern to the SMG shift pattern. This is also this is a 4 input, 4 output mechanism. So we have 4 available inputs and 4 outputs. So now we'll talk a little bit more in depth about the transmission side mechanism. This is the motion pattern that comes from the output of our driver interface mechanism. Now you'll notice that it's flipped across the X and the Y axis from what would seem to be an ideal human interface. This is because of the spherical bearing in our driver interface, and we'll talk more on that later. But the goal of our transmission interface mechanism is to go from this motion layout to the SMG layout. Now you'll notice on the SMG layout, gears are not where you would expect them to be. So we have 2nd gear and 4th gear on one slider. If we have 5th gear and 3rd gear on another slider. Additionally, you'll notice that 6 and 7 are on the same slider, but they're flipped in relation to this pattern, and same with first and reverse. So now I'll talk about the sub-mechanisms a little bit. So circled in yellow are the inputs to our transmission mechanism. Now these all translate along the length or the long axis of the transmission, which is parallel to the transmission tunnel. We have a pin on each one of our sub-mechanisms that will interface with an input linkage, which is to be designed next semester. But each one of these is in line to line up with the outputs of the driver interface mechanism, so we won't have any crossover in our connecting linkages. Like I said earlier, each input has 3 positions: neutral, engaged in one gear, and engaged in a 2nd gear, in this case, first and reverse. Now you can see how the inputs correlate to the output slider motion on the other picture here. I know this is, you might not quite have a grasp on how this thing works, so we put together an animation here to kind of go through each step as the driver would shift through the gears. We start in reverse. The red circle here indicates where the shift knob would be in the interior of the car, and the red circle on that side indicates where the output slider is traveling to as the gear is engaged. So reverse would be pushed forward in this case. So we'll start here. This is the reverse first input, and then we'll move across the mechanism. So I'll start the animation. We start with reverse. You can see it's pulled down, engaging reverse. We're pushed up for first. Then we move over to our 2nd, 3rd cam. We go down for 2nd, and then up for 3rd. Then we move over to our 4th, 5th cam, down for 4th, up for 5th. Then we move over to our 6, 7 reverser, down for 6th, and up for 7th.
So let's start with the reverse and first gear linkage system. This was located on the top right of the cam plate. So on the left here, we have linkage synthesis with 35mm output input and 16mm output. And this is essentially a 4-bar linkage double crank rocker. And on the right here, we have the linkage mechanism design. So this is just a preliminary design to make sure that the linkages fit in the housing, and further evaluation would have to be done in the 2nd semester to make sure all the parts pass criteria.
Onto the cam design. So this was iteration 1. And if you look here in the picture on the right, the simplest path for a cam is to have a straight slot, and which is not really ideal for our needs. So if you look at the graph on the left, it shows input force over input displacement. And what you can see is as the cam begins to turn, the input force needed to engage that cam quickly drops off, resulting in a nonlinear shift field, which leads us to our second iteration.
All right, so the second iteration of the cam design, we implemented a 22 millimeter radius on our slot going from state 1 to state 2 on the cam. As you can see here, we've plotted output displacement versus input displacement. It's very linear, and the slope is equal to our desired mechanical advantage. We have the same graph that was shown here on the previous slide. So this was a test with a constant output force versus the input force. As you can see here, it quickly jumps up and is constant all the way across. And then going on to the last part of the mechanism, the 6-7 reverser. This is similar to the reverse and first mechanism, which we have to reverse the action of what's happening due to the shifter interface. So actually, initially, we wanted to make vertical reversers, but with our constraints for the transmission tunnel, we could not do that. It took up way too much space. On the left, we have another linkage synthesis with 35 millimeter input, 16 millimeter output. And if you could briefly see the 2.94 millimeter and the 6.43 millimeter construction lines right at the end, that is the distance of the slots right here for the input, and this is the output. So we'll have the rod going from the driver interface straight connected here in the slot, and it will just pivot along this lever. And right here on the bottom, we have the Hertzian contact stress. This material, we used 4340 steel, and this resulted in a factor of safety of 2.4. And going on to the lockup mechanism, this criteria actually satisfies one of our constraints where we can't have two simultaneous gears engaged. Right now, the twin cams actually cannot engage at the same time, but this lockup mechanism prevents any gears actually simultaneously engaging. So in the video, we'll see that this horizontal bar has pins sticking out of it, and on the top of the output rods, there are 3 slots with up, middle, and then down. So the green output rod is the 2, 2, and 4 shifter interface. So we'll see as we're shifting down, the pin goes into the upper slot, and all the other pins slide into the middle slot, locking all the shifter interface to prevent simultaneous engagement of the gears. All right, now to talk a little bit about the driver interface mechanism. So this is the first iteration of our driver interface mechanism. This was created purely for geometric testing as well as some selection mechanism testing. I actually have the 3D print of it here. We created 2 syntheses. One synthesis was for the longitudinal throw. This is engagement of a gear. And then the lateral throw, this is the distance between gears. We used this as a test bed for a couple of different shift gate ideas, and eventually settled on this one, which we 3D printed and tested. Additionally, you can see the output mechanism here. This was created to prove the concept of this geometry to make sure it could operate smoothly. And as you can see, it shifts between gears without much interference from the output mechanism. So these are some pictures of my actual M5. We put the 3D printed shifter prototype into the center console, and we each sat down in the car and felt the positioning of the shifter as well as the throw and lateral movements, and decided that the geometry that we had picked that was heavily based on the C7 Corvette is ideal for this car, and felt like it would make for a very engaging shifter.
Now on to the second iteration. The main difference is in this lower assembly, and I'm going to pass this one out that you can play with, and if it gets stuck, just make sure these are equal, but it's a little fragile, so be careful. But otherwise, so the main change was in this lower assembly that you can see here. We wanted to seal, or to start off with our synthesis of the second iteration. Based on prior calculations, we needed a 35 millimeter output throw out of the these rods out of the bottom of the shifter. To accomplish that, we had to lengthen this bottom of the shifter below the pivot ball 4.14 millimeters, which additionally spaced out our lateral travel, which made the slots a little wider, which wasn't a big deal. Where the major change came from was trying to make this a fluid-filled system to reduce friction within the assembly. To do this, we needed to transition this rectangular output rod into a cylindrical output rod so that we could fix cylindrical shaft seals on the end of this assembly to retain all the fluid we fill it with. In doing so, with one of the smallest seals that would safely transmit the force, it increased the base and the width of this lower assembly, but we were able to accomplish that goal of having that fluid fill with iteration 2. Now on to, as we lead into our spring semester, there is a fair bit of work we still have yet to do. We're going to be working on an iteration 3 of this lower assembly. We're going to be found, after looking at this, there's no need for this added length within these selecting rods. So we're going to cut out about 1 inch of material to lower our cost of material and save time in manufacturing. Additionally, we're going to cut out the 290s on this selector rod mirrored on both sides, make it more of a diagonal to make it more manufacturable, as well as cut out this boss and have the cylindrical rod threaded to the square output rod. Another pain point with this design was right where the spherical shift ball connects with the rectangular output rod, we have a point contact there, which is not great. We ran the Hertzian Hertzian contact stress on the point, and we found 352,000 psi of pressure on that point using 304 stainless steel for the shifter and a mild steel for the rectangular rod. So that gave us a factor of safety of 0.1, which was not ideal. So we had to brainstorm a different way to transmit that force effectively. And so we leaned back on our research, and on the 82 Supra, they use a plastic bushing on the end of the spherical output rod that transmits their point contact makes it cylindrical contact on their selection rod. But we couldn't do that since the height of our spherical ball changes based on gear position. So we are going to use the pivot from this, as well as have a rectangular contact patch on here at a size of 2 mil by 2 mil, which will result in just a normal contact, giving us 3,800 psi of pressure and a factor of safety of 8.2. And then additionally, we're going to work on a lateral force mechanism. So we have the engagement force, but we don't have anything to give us a nice linear feel for the lateral force. We're going to design that. We're going to design the linkage that connects both interfaces, as well as seal the transmission interface to prevent salt and any gear oil getting out of that transmission. Then we're going to do a final analysis and optimization of most of our components and look at a lot of FEA.
All right, any questions?
I might have been fine with the mock-up when you said this, because I think you did, but a couple of slides back, you were talking about a fluid filled.
Yeah, that whole lower assembly we're going to fill with fluid to reduce the friction within it.
Fluid?
Some gear oil, probably a 75, 39.
It may not even be necessary to do a gear oil, maybe even just like a light grease, something along those lines.
Yeah, because if it's oil, then you have to seal it.
Yeah.
Real well. So primarily for ease of motion. You said you were targeting 80% efficiency. That's in this part of the system.
Yeah, so that includes from the driver input to the output that actually moves the
This
force.
output, or there are a couple steps down the line?
A couple steps down.
Okay, so how many joints, connections from driver's hand to your final?
It depends on which linkage. I think the worst case would be the reverse linkage, or the first reverse linkage, which would be seven rotating pivot points.
Okay, so about 3%, about 97% efficiency through each joint, more or
I
less?
hope so.
Yeah, so that's, I think that's 80% is a realistic target, and I think you understand.
Yeah, when we
might
set
have to
that,
do some special things with that many connections.
when we set that goal, we didn't have a mechanical design in mind, so we didn't know if we were gonna end up with, say, like a bushing, which may have more friction or large sliding surfaces. I think where we've gone with the design is very good in terms of transmission efficiency. We've very heavily focused on making sure that we're trying to reduce friction at every point.
Yeah, that's it. With that many connections in the system.
Yes.
The amount of background work you did upfront with testing different cars and assessing what your design targets, what your design objectives are, that is also really very good.
Okay, couple of questions. Question number one, maybe you don't have an answer to. But lot of these driver interface points on vehicles have a lot of ergonomic opinionated customers. People will say the feel of the ship, and no one knows how to quantify. Did you read or study any of that ergonomics aspects of the ship?
No, I think we mainly used using the different vehicles to find an ideal kind of ergonomic pattern to build upon that. It may change slightly between our final model, and I mean, we also could extend the length of the shifter if the customer wanted a long throw, or decrease it if they wanted a shorter throw. But we do still have some freedom within there to meet any opinions of the customer.
I think I might have a different answer to your question. Well, not contradicting, but so you're talking about the feel as you engage the gear, like the actual mechanical kind of
Or
like the chunk as you
reaching
engage
to
it.
the shifter and then the feel of engaging in this.
Yeah, so the reach we did consider. Actually, BMW did most of the considering for us because they put the shifter in hole in the right spot. So we did consider the throw. That's what Cole was just talking about. As far as the feel of the actual mechanical feel of engaging the gear, that's kind of a more tricky problem because we didn't design the transmission itself. We have done some preliminary testing just basically with a lever to push the shift works in the transmission, and the feel is actually very good. If we just kind of simulate the mechanical advantage of our mechanism, so we're hoping that feeling isn't lost, but yeah, it is, like you said, it's very opinionated. So I have my own opinions, Cole's got his opinions, so we're trying to meet somewhere in the middle. But yeah.
The second question, maybe I missed this in the beginning. What's the core motivation driving this project?
Okay, so we didn't put this in at the beginning because this is another one of those very opinionated problems. So Dr. Sebastianis can attest to this because he actually owned one of these cars for several years. I've owned mine for almost 2 years now. It's a very interesting transmission. They're not a dual clutch, so it's just like if somebody was sitting next to you driving a manual transmission, but you have none of the control or the feel. All you can do is tell the computer to shift, and it will shift. This leads to kind of some clunky and what's the word? Like clumsy shifting, like letting the clutch out too fast sometimes. Sometimes it'll even like chirp the wheels as you pull away from the stop sign if it thinks you're gonna go for it and you don't.
Unintentional.
Yeah, so it's like if you imagine you have a passenger who's blindfolded and he's running the clutch and the shifter, that's pretty much how it can feel sometimes when you're going slow. Now, when you're really getting on the car, that's where they optimize this transmission. So at full throttle, shifting on the red line, it's crisp and smooth. It's fairly hard shift, but it's nothing you wouldn't expect from a manual transmission.
That's a city driving very like hesitating, almost like pausing as you shift. You just wait for it to shift. You can easily shift it faster manually, but at the higher RPMs, it's excellent.
Yeah,
Yeah, the shift speed in the SMG program is directly proportional to the throttle position. So if you're just cruising, it might take almost 2 seconds to make a shift from the point of putting the clutch in, shifting, and letting the clutch out, which can sometimes be nice because it's very smooth, but it can also feel kind of strange, especially if you're not used to it.
For city driving also, and the majority of driving, it's not, I guess, fun. Yeah.
Yeah, another factor we mentioned was the decreased reliability of the electrohydraulic unit, because that's known to cause problems and people tend to replace them, and those units cost about $10,000 each.
So that would be something good to quantify. I know it's
Yeah.
not easy because it's a commercially manufactured vehicle with a lot of proprietary information, but we think it would have some quantification for that reliability.
Yeah, I think for the final phase of the project, we're gonna look kind of at, I don't want to say an economic analysis, but like the basically the economics of the process. So there is a manual transmission option for the M5. It's actually a transmission from a different car. They're very expensive and they require some other modifications to the car to make it work. So our goal is basically to come up with a solution that is basically bolt-on. So that's I just completely lost my train of thought. Sorry.
The motivation and
That's the-
Oh yeah, yeah.
quantifying.
So the cost of the transmission, and then compared to our project, as well as the cost of our project compared to replacing the hydraulic unit. That's where we were going with that. Sorry.
Yeah, thank you. Okay, that's the end of the presentations. It's going to be time for a short break. Thank you for all presenting your work.
Yes, very nice.
Appreciate it, yeah.
They're all very interesting. Thank you, sir.